Sorry. Okay. So number 8 and number 11, let's look at that. Yeah, they're related questions. Okay. So they're both questions about finding the most general antiderivative. And really, when you're thinking about the general antiderivative, remember that means it means the plus c, right? You don't know exactly what the antiderivative is, so you need to have a plus c there. In number 8, sorry, which was the question again? Let me look here. Yeah, number 8. So they tell you f of x is 9x to the 9th minus 4x to the 6th plus 10x cubed. And you know, those numbers may well be different for you, but they'll be similar. So these, when we have sums or differences, we can break those apart into, right, separate antiderivatives, because that's the way derivatives work, right? An antiderivative is just reversing the derivative. So whatever antiderivative is here, when I take the derivative of it, it won't interact with these other pieces. So the antiderivative of 9x to the 9th, our general rule here with polynomials is that I'm going to add 1 to the exponent and divide by that new exponent. And I'm going to keep the constant in front. And it says here you should check your answer by differentiation, which just means let's take the derivative of this, and we can see from our derivative rules that we would get the 10, which would cancel there, subtract 1, and we would get back exactly what we started. So I'm going to continue that process here. Add 1 and divide by that new exponent for each of those, and constant multiples are fine. They can just be pulled out in front. We don't have to take an account of those. And of course, if I put this in, excuse me, if I put this in, what will happen? I'll get it wrong, right? Because what did I forget? Well, not finished, right? The plus c. Now, you will also see some problems where they ask you for a specific function. And that's really actually like it's called a differential equation. But if I tell you another piece of information here, if I tell you, for instance, and you know that f of 1 equals, well, yeah, it's a little bit of a messy example, but let's say f of 1 equals 2. So if you know this additional fact, remember if you looked at what we went over on Tuesday, this is a whole range of functions, right? All of these functions, because we know the derivative, we know the shape, but we don't know the specific function. It could be any one of these functions, right? But if I tell you a little piece of information, I say that f of 1 is 2. Well, it turns out there's only one function that has that exact shape that goes through that exact point. So knowing this one piece of information, we can find the value of c, and that'll give us what's called the solution to this differential equation, which is basically like I'm telling you the derivative and I'm asking for the original function, not just the general one. So what I would do in this case is I would put in 1 here for x, and I would get 9/10 minus 4/7 plus, well, let that'd be 5/2 plus c, that should equal 2, right? And then I'd go through here, it'd be slight hassle just because of these, right, awkward numbers or fractions to deal with. But you'd find c, and then you would know exactly what the function is. So if you have an initial condition, you can use that to figure out exactly what that function is. So as long as you have, so the question is for that rule, yes, that is true, as long as you don't have a product or quotient or something else going on. As long as you just have like a constant times a number, a power here, then you can use that general power rule, which is add 1 and divide by the new number, right? Rather than subtract 1 and divide by, multiply by that, and then have the subtract 1 as your exponent. Sorry, bad way of describing the derivative rule, right? But the antiderivative rule is you add 1 and then divide by that new power. And that works for all, it works for square roots and negative exponents, except for x to the minus 1, right? That one it doesn't work for. And then there was also a question on number 11. So same general question, find the antiderivative. But a different kind of function. Right, but just like before, sums and differences are nice because I can separate that into 2 different types of problems. As I was just saying, this is really 2x to the 1/2. So when I take its antiderivative, I'm going to add 1, which is going to give me 3/2, and then I'll divide by 3/2. And you can see how the derivative is going to undo that. Get me right back where I started. The 5 here, I get to just keep as a constant multiple. And then the antiderivative of cosine, it turns out is sine. The derivative of cosine gives you a negative sign, but the antiderivative of cosine is just sine. And again, I'm checking it mentally by taking its derivative. The derivative of sine is just cosine, so that works. And then I'm remembering to put in my plus c. Okay. So it is a little bit of a new way of thinking, right? And it takes a little bit to get used to that. But the advantage that we have is that we already know about derivatives. And so we are able to check our antiderivatives. We can check this work and verify that it really does work. And so that's a powerful tool to kind of help you as long as you are close. Now notice neither of these would have worked if I had had a product, right? If these 2 functions were multiplied together, all of a sudden I'm out of luck. I don't know how that antiderivative would work. Because the derivative of a product is of course quite, well, a little bit complicated, right? You have derivative of the first times the second plus the second times the derivative of the first. So you don't get to treat them independently if they are products or quotients. Any other questions on?
So you just leave your answer like that, right?
Well, yeah, I mean, I guess that would be fine. I think you should, I guess you should probably simplify that, right? That's really 4/3 x to the 3/2. But yes, you're looking for the function, right? What function or what class of functions has a derivative that equals little f? any other questions? Okay. We will practice more antiderivatives and learn more about antiderivatives at kind of the end of chapter 5, so kind of 5.4 and 5.5 a little bit. But these are kind of the building blocks of those. So understanding the kind of forward and back nature of derivatives and antiderivatives, right? And that's important. And I would again encourage you all to remember the C, because you will find some where you do all the work and you get it all right, but you forget the C, and you will be upset, right, when it marks you wrong for something like that. Okay. So 5.1 is the area problem. And, you know, when we introduce calculus, or I introduce calculus in the very beginning, day 1, day 2, we talk about our two big problems, which were the tangent line problem. We have this function and we have this tangent line. We want to find the slope of the tangent line. And we've spent a couple of months, right, figuring out how to solve that tangent line problem, developing the limit, and then seeing what that problem actually does for us, which is certainly a lot more than you would have thought in the beginning, right? Finding the slope of the tangent line seems, well, not all that interesting really, but it turns out it tells us so much about functions and their mins and maxes and what it looks like. It tells us a lot about what we want to know. So it's an important tool. The same holds true for the area problem. So the area problem is the second problem that we have. We're given some function and we'd like to find the area between A and B. Now, in a very small number of circumstances, you can find the area if it was like a semicircle or a rectangular shape or maybe some sort of triangle, you could find the area, right? But if you have some curve like this, we have no geometric formulas or tools to find that area, right? But we can try and approximate the area and then try and make our approximation better and better and better. And you hopefully, I'm hopeful that you remember that that's what we did with the tangent line. We couldn't find the slope of this tangent line directly, and so what we did is we said, well, okay, let me find the slope of this line, and then let these lines get closer and closer and closer to the tangent line. And that limit of these slopes turns out to equal the slope of the tangent line. So even though we couldn't get there directly, we were able to use the limit to solve that problem. And we're going to bring a very similar approach to this area problem. The limit, remember, is really the vehicle or the tool that creates calculus. And we're going to use it to solve this area problem as well. Now, I'll tell you that when I do lecture on 5.1, it kind of blends into 5.2 a little bit. These two chapters are very much connected, and so you know, sometimes some of the ideas I talk about, we don't really see the problems in 5.2 and vice versa. So you know, if you don't see some of these in the homework, don't worry, it'll show up in 5.2. So let's say I have, well, let's look at it visually. I want to find the area under this curve. And as I said, I can't find it directly, but I can approximate it. There'd be lots of ways of approximating this geometrically, right? You could set up some kind of trapezoids or different shapes, but it turns out that for us, little rectangles are actually, in some ways, almost the most useful method here. So I drew here 5 rectangles, not a real excellent drawing. They should probably be kind of the same size. But what we can see is that if I add up the areas of these 5 rectangles, I would certainly get something reasonably close to the area under this curve, right? Especially because some of them are a little bigger and some are a little smaller. It feels like this might actually be fairly accurate. Now notice I had to figure out the height of each of these rectangles. What I tried to do was when I looked at the rectangle, I just went up the left side and used wherever that hit the function as the height of that rectangle. A little hard to see from my picture, right? And so what I can think of here are these values. This is called a partition, dividing the values between A and B into parts. Call that x0, x1, x2, x3, x4, and x5, right? So when I have 5 partitions, 5 rectangles, we're going to think the first value here is x0 and the last value is x sub 5. And so if I want to come up with a sort of formula for what I'm doing here, what I'm doing is I'm taking the height, and this is an important idea here, the height of this rectangle is exactly the function value at x sub 0. So I'd take f of x sub 0. This would be the height of that first rectangle. And then I would take the width. Now, and this is maybe my picture. I could have been a little better with my picture. It's easiest if I just make all these rectangles the same width. I don't have to actually, but I don't need to make unnecessary work for myself. So if I make all these rectangles the same width, one way to write that down is to say b minus a, that's that distance here, right? Larger value minus smaller value. And then I wanted to divide it into 5 pieces, right? So 1, 2, 3, 4, 5 chunks. So this is equal to the width of each of those rectangles, and I'm going to call that width delta x. Okay. So I don't know what B and A are or F is, right? Those are going to change in these different problems. And it won't always be 5 rectangles, right? It could be 10 or n or a million, right, rectangles. But whatever I calculate here is my width, and that width, right, is going to be the other dimension for that rectangle. So I'm going to write that down as just delta x, right? Delta x is this value, b minus a divided by 5. So then I want this total area, so I'm going to add, this is the area of the first rectangle, and then I'm going to add the area of the second rectangle. So for the second rectangle, I'm choosing this value to create my height. So it's going to be f of x sub 1. The width is going to be the same. And I just keep going, right? I want 5 total rectangles. 4, so one more, f of x to the sub 4 times delta x. And if I add all of those together, what I get is an approximation for the area. any questions so far? I mean, a lot of it really is, it's not a revolutionary idea at this point, right? I'm just adding rectangles together. There is some notation here, right? Like how I write those parts. But it should be, you know, it's just adding the areas of the four rectangles together. Now, I claim that's an approximation. It certainly is some kind of approximation. Is it a good approximation? Well, that's a very subjective word, right? Good, I don't know. It depends what my goal is. If my goal is mathematical, then I'm like, I don't really think of good. I want the actual area. I don't really want an approximation, right? That to me leads to unknowns, right? And we like to have knowns. We like to know what things are. So the question is, could I kind of reuse this idea here with the area problem, right? This red line was an approximation to the true tangent line. The way to get the true tangent line was to make better and better and better approximations and then use the limit to see where those approximations are going towards. What is the actual slope here? And hopefully, what is the actual area here? So what would make this a better approximation? And there are many correct answers. You know, one option would be to maybe use trapezoids instead of rectangles. Right? Like maybe if I made this kind of at an angle rather than a rectangle, that would sort of be less error. And that is true. I could use different values for the height of the rectangle. Maybe I use the midpoint. That would give me a rectangle that sort of over and underestimates together. So that could also be a better approximation. But it turns out that for our purposes, a really nice way to do it is to just make more rectangles. Right? Rather than having 5 rectangles, what if I made 10 rectangles? Each of those rectangles would then be sort of half the size. My picture here is hard to see, I think, right? But it would basically cut out kind of half of the error here. More rectangles would give me more accuracy. And then we could argue again and say, well, okay, 10 rectangles is good, but there's certainly still some error there. Could we do better than that? Well, sure, why not do 20 or 100 or 1,000, right? With a computer, that's no problem to do those calculations. But still, those are all estimates, right? Now, the important thing is that those estimates are going to be getting closer and closer and closer to the true area. Okay? Every time I add more rectangles, I cut out some error. That means it's getting closer and closer to the true value. And something that is getting closer and closer, something that we can make as close as we want to the true value, means we can find that true value by taking the limit. So that's where we move past a sort of simple calculation where we're just adding up rectangles to a calculus calculation. Okay, and let me write that down for you, and then we'll kind of unpack what I've written down. So we're going to state this as a definition. We're going to say the area under the curve f of x from a to b, x equals a to x equals b, is equal to the limit as n goes to infinity of f let me write it as f of x sub 1 times delta x plus f of x sub 2 times delta x. And I'm going to keep going all the way to f of x sub n times delta x. Now you might be thinking here, but wait a second, the last time we started with 0 and we went to 4, here you're saying let's start with 1 and go up to n. So n is representing the number of rectangles or partitions. So here I went from 0 to 4. It turns out in this definition it's going to be easier for us to use the right endpoints. And we could illustrate that more clearly, but as these rectangles, maybe I can do it a little bit, as these rectangles get smaller and smaller and smaller, right? As I add more and more rectangles, this would be f of x sub 0, and this would be f of x sub 1, right? So here there's like a difference between them, right? This f of x sub 1 is certainly a little bit larger than f of x sub 0. But as the interval gets smaller and smaller and smaller, right, the number of these rectangles starts to go to infinity. Each of these intervals become very small. It turns out that the left and the right endpoints, it doesn't really matter anymore. The heights are are all going to the same values. And it turns out for our calculations, it's actually going to be easier to use the right endpoints rather than the left endpoints. All this is saying is I'm going to add up the rectangles. Each of these is the area of a rectangle. And then I'm going to let the number of the rectangles go to infinity. And whatever value that's heading towards, that is equal to the area under the curve. So that is sort of a big jump, right? To say like, okay, we can approximate the area. No one would really argue with that. But you have to have an idea of what the limit is doing in order to understand what this is trying to tell you. Now, in order to actually do this, I'm not able to calculate the limit when I have this sum written out like this. This is called an expanded sum, right? I have this, plus dot, 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 plus this. So it kind of implies what's in there, but it's not a kind of function that I'm able to calculate, because these x sub 1, x sub 2, x sub n, those are changing. As n gets bigger, each of those gets smaller, and the delta x's are changing too, right? That's the width. So those are getting smaller and smaller and smaller. So I still have some work to do here to actually come up with something to calculate, but I hope that we understand what this is telling us. Are there questions about this? Is this believable that this expression would actually give us the area under the curve? I mean, you have to kind of trust the limit tool, right? To say that even though we never get there, right? We never get to the true area because there's always a little bit of error, that the limit is actually that true error, right? There's some sort of intellectual jump there, right? Approximations are no problem, but the idea that the limit exists is definitely more subtle. It could keep you awake at night, right? Okay, so let's see if we can reformat and rework with this in some sort of way that that allows us to actually calculate the limit. So here's a couple definitions I'm going to make. First of all, let's let delta x, just like I said before, equal b minus a over n. So that's what we did here, right? We divided into 5 pieces to find our width, but now our number of pieces could vary. Okay, and then we need to come up with some kind of an expression for x sub I. And x sub I could be x sub 1 or 2 or 3 or 100 or 1,000, right? And so the formula here for x sub I is we're going to start at A, and then we're going to add one of these widths each time. So if we sort of imagine that we're moving along this partition, this is A. X sub 1 is right here. It's like the next one. X sub 1 is going to be A plus a delta X. So there's the delta X is the width, right? So when we go to A to X sub 1, this is going to work. X sub 2 is going to be A plus 2 delta X's. So there's one delta X there, and there's another delta X there. And if I add 2 of those together, I get to X sub 2. So this little formula here is going to tell me the right endpoint of each of these intervals, no matter if I have 100 or 50 of these, or 1,000,000 of these. Now, the other thing that I have to kind of formalize are this adding up part, right? I want to add up each of these, and I want to go from the first one up to the nth one, right? That's the last one I want to add up. And so what we need to do that is something called sigma notation. And I posted a little video from my favorite online source about sigma notation. So you should definitely look over that. It's just a mathematical tool to help us do these sums. So sigma is the Greek letter S, stands for sum. So sigma notation, the way it works is we put this sigma, that just means sum, add up. And then what I do is I put a little counter here. So I want to go from I equals 1 to n. So I is like a dummy variable, and it's going to start at 1. I can have it start wherever I want. It can start at 20 or negative 15, but I want it to start at 1. And then I want it to go, then it'll go to 2, and then 3, and then 4, and all the way up to n. Right? So, and then I need to tell it what kinds of things to add up. And so what I wanted to add up are these things, right? I want to take f of x sub I times delta x. So this expression here gives me exactly this expression here. These are the same things. This is written using that sigma notation. When I equals 1, I get f of x sub 1 times delta x. And then I'm going to add to that when I equals 2. When I equals 2, I have exactly this term. And it's going to go all the way up to n, the last one, right? F of x sub n times delta x, and that's the last one there. So this is a way of writing this part of the information. And then, you know, to put it all together, I need this limit, right? Because I need to let the number of these rectangles go to infinity. So area is defined as the limit as n goes to infinity of f, sorry, this, let me just start over. I messed it up, and it should look better. So the area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times delta x. And I'll write it in here again just because it's worth writing it in here. Delta x is b minus a over n, and x of I is a plus delta x times I. So this is kind of heavy notation, right? This limit and sigma and x of I and delta x and all this stuff. But it is a way of communicating our idea efficiently and in a way that we're going to be able to work with mathematically. So it is very important to me that you understand what this is saying. This is adding up the areas of the rectangles and then letting the number of those rectangles go to infinity. And if we do that and can calculate where they are heading, right, the limit of those, that will tell us the true area under that curve. Now, in order to be able to do that, I need to be able to do some things with the sigma notation. So that's why you need to sort of look at that video to check that out. And I need to kind of work with some other tools here to figure out kind of how to calculate and actually do this work, right? And that's what we've talked about through the course, is that calculus is both parts, right? It's understanding the idea behind the calculus, but then there's also the execution part, right? The algebra and the formulas and plugging the values in to get a number. I think what you'll find when you look in the 5.1 homework is that they don't ask you actually to do any of those calculations yet, right? So we'll save those till 5.2, and we'll talk about that more on Tuesday. But they do ask you to kind of set some things up. So for example, if I want to find the area under f of x equals x cubed plus 1 from x equals 1 to 3, then what I want to do is be able to set this up. So the area under the curve is going to be the limit as n goes to infinity of the sum from I equals 1 to n. So that's the same no matter what the function is and where it's located. But then I need to figure out what the x of I is and what the delta x is and put those into the function. So delta x we have to figure out first. That b minus a over n. 2 over n. So the width is 2 and I'm dividing it into n pieces. So each of those has to be 2 over n wide. X of I is a. My a value is where I'm starting, which is at 1. Plus delta x, which I found 2 over n times I. So now what this tells me is that I'm going to put x of I in place of x. So my function was x cubed plus 1. So this is going to look like 1 plus 2i over n cubed plus 1. That's f of x of I. And then I'm going to multiply that by delta x, 2 over n. So this is the expression that I'm trying to calculate or figure out in 5.2, but for right now, that's the setup that I want you to be able to do. Okay, you'll see different functions and different intervals, but the process will be the same really for all of those. Okay. The other thing you will have to do, which is a little more numerical, like just calculating values, is they'll give you a function like x squared and say, let's approximate the area with, let's say we're going from 0 to 2 with 4 rectangles. And let me see how they phrase this exactly so you know. Yeah, and then they'll tell you typically that you should use, right endpoints or left endpoints. Not too many of those. The estimate is going to vary whether I use the right endpoints or the left endpoints. So if I divide this into 4 rectangles, right, I have this, and over this interval or partition, I can choose to use the right endpoint as the height, which would give me this large rectangle, or I could use the left endpoint as the height, which in this case would give me no area because it's at 0. And I could move through the rest of the intervals that way too, right? The red here is using the left endpoints. And the blue would be using the right endpoints. Right, and from this graph, I can see, well, certainly the blue endpoints are going to be an overestimate, and the red endpoints are going to be an underestimate. Okay. Now, both those estimates will get better as n goes to infinity, and it turns out they both go to the true area. So it doesn't actually matter in our definition whether we use right or left endpoints, but it turns out to be easiest. This formula turns out actually to be the easiest one for us to work with. So all I would do here is actually just physically calculate what the area of the 4 rectangles are, right? Whether I needed to use left endpoints or right endpoints, I would get different estimates, right? But I would just add the values together. So this would be f of 1/2, because that's that first interval there, times the height, which is, that is the height, times the width, right, which is 1/2. And then I do f of 1 times 1/2, etc. Right? And my function is this. So I just put in, right, 1/2 squared, 1/4 times 1/2, 1 squared times 1/2. Right? Add those all up, and that would equal my overestimate, right, or my right endpoint estimate. And then I would also, of course, have one for the left endpoint if that was what was asked. Questions about this and this process at all? We're still missing some of the tools to actually, like I said, to actually do these calculations. We need to know mostly just how to work with this sigma notation. Like, what does that do? How does that operate on an expression like this? It's not super difficult, but it is new, and so that always takes us a little bit of time to do. Once we can figure out how that sigma thing works, we can calculate this and get an expression, and then we can take the limit. And luckily we've done quite a few limits already, so we will know how to find the limit, which will give us a value, and that value will be what we're looking for, the true area. Now, you may be thinking, who cares about the true area under the curve? Maybe you're not thinking, maybe you're just saying, well, that's what I have to do, so I'm just going to do it. But I think it'd be a very legitimate question to say, why is the area that important? Well, it turns out in the same way the derivative told us a lot more than we thought about the function. The area will also tell us a lot more than you might think about the function. You'll also see that there's a connection between the area and the derivative, right? It doesn't seem like there should be, but they are connected. And we'll learn that in 5.3, called the fundamental theorem of calculus. Okay, so that should cover the main ideas in the 5.1 homework. And actually probably even get you started on 5.2 homework as well. So, remember to work through the 4.8, 4.9 homework, and then get started on this 5.1 homework. I am certainly always available for questions, and I will work on getting the lecture capture back up and running, or some version of it where you can see those. But until then, just look for those little videos on D2L, and I've added some more to what was already posted. And as always, let me know if there's not enough, if there's something else that you'd like to see. I'd be happy to make one or find one that fits your question. Okay. Okay, so I will let you go. Hope you have a good weekend full of productive calculus studying, and I also hope to see you all on Tuesday. Yes, thank you. Thanks for coming. Take care.